When humans describe a work of art, architecture, or nature, we often do so in terms of symmetry. We can do the same thing with algebraic functions. Symmetry is related to whether a function is even or odd. So let's take some time to understand the definition of an even and an odd function. Number one, a function is even if f of negative x equals f of x. Now consider a graph. I'm just going to look at a basic parabola, rough sketch here. We'll consider our parent function y equals x squared. So notice right here, I may have ordered pair 2, 4, and on the other side of the graph, we have ordered pair negative 2, 4. Our algebraic test here says if I can change the sign of the argument, notice we went from argument negative x here to argument x, so I've got opposite signs for my x values. Well, it says the y values, remember f of corresponds to y, f of negative x equals f of x. And this says the y values are the same. So even though the x values are opposite in sign, my y values have the same sign. This places the point on either side of the y-axis at the same elevation. So this generates a function that is symmetric about the y-axis, just as our parent function y equals x squared is. On the other hand, a function is odd if f of negative x equals negative f of x. For a moment, let's consider our cubic function. Again, kind of a rough sketch here, but we'll look at the function x cubed. Let's consider the point 1, 1 on our cubic function and negative 1, negative 1. In our algebraic test, notice the x values have opposite signs. I have a negative x input and I have a positive x input. So if I compare the x's on these ordered pairs, they are opposite in sign. But if we look at the y values, the f of negative x, now it's equal to negative f of x. So notice the y values are opposite in sign. One is positive and one is negative. So look, this y value is negative and this y value is positive. So points with opposite x values and opposite y values generate a certain type of symmetry. Now, we said even functions are symmetric about the y-axis. You might want to say, well, then odd functions must be symmetric about the x-axis, but that's not true. A function that's symmetric about the x-axis is not even a function, right? It wouldn't pass the vertical line test. But back to our example here. If you have opposite y values and opposite x values, this actually rotates the point around the origin. So we say odd functions are symmetric about the origin. Let's take a minute to go back through a few of the graphs in this section of notes and use symmetry to determine if the functions are even, odd, or neither. Let's go all the way back to our library of functions on the first page of this section of notes. If we look at our identity function, y equals x, notice I can take one point and rotate it around the origin to find its reflective point, or I can do the same here with this one. So we would say this function has origin symmetry. Therefore, it is an odd function. If we look at our quadratic function, as we mentioned before, we can fold this in half on the x-axis and have two matching pieces. So this has y-axis symmetry. Therefore, we say it is an even function. If we consider the graph of our cubic function, y equals x cubed, notice it has that rotational symmetry again. So it has origin symmetry or symmetry about the origin. Therefore, we say it is an odd function. Scrolling back up here to look at our absolute value of x function. This one we could fold in half on the y-axis and observe y-axis symmetry. Therefore, it is an even function. So the identity function is odd, the absolute value function is even. The square root function has neither type of symmetry because there's nothing over here on the left side for it to reflect or anything down below here to create either y-axis or origin symmetry. This one is neither even nor odd. And our last example, we have a cube root function. Notice it has the rotational symmetry. So because it has symmetry about the origin, we say it is an odd function. Okay, back to example 8. Now let's algebraically determine if the following functions are even, odd, or neither. Notice we want to algebraically determine the question. Then we can graph the function on our calculator and use symmetry to visually verify our conclusion. So to determine if something is even, odd, or neither, we're going to apply our algebraic test. Notice in each case, we begin with f of negative x. Depending on the result, we can conclude if it's even or odd. So we're going to calculate f of negative x. That is, we're going to replace all the x's in the function with negative x's. Now, if we take negative x and raise it to the third power, that gives us negative x cubed. Multiplying that by negative 2 gives us the term negative 2x cubed. And minus negative x gives us a positive x. Now, take this result and compare it to the original function. Notice each term changed sign. So this is the opposite of the original function, negative f of x. So looking here at our algebraic test, we found out that f of negative x is equal to negative f of x, that is every term changed sign. Therefore, we are dealing with an odd function. So example A is an odd function. This means that the graph should be symmetric about the origin. So let's take a quick peek at the graph. We have 2x to the third power minus x, and we're going to graph it in our standard viewing window. Notice it looks like our parent function, x cubed. It's just got a little bit more of a pronounced curve, but we can see it is symmetric about the origin. Therefore, our conclusion that it was odd is correct. Let's try our next example. We want to find g of negative x. So we're going to replace all the x's in the function with negative x's and then simplify. Negative x to the second power becomes positive x squared. We could write plus negative x more simply as minus x and plus 1. So we plugged in negative x and we simplified. Now we want to compare it to the original function. Now, the first term stayed the same, the second term changed sign, and the last term stayed the same. So it didn't stay exactly the same. If after I simplify, I get exactly the same thing, we would end up with an even function. Or if all of the terms changed sign, we would have an odd function. But neither of those occurred. So in this case, we can say our function is neither even nor odd. So let's take a look at the graph of this one. So I'm going to go to y equals and type in our function, x squared plus x plus 1, and graph it in the standard viewing window. So this curve has a type of symmetry, but specifically I can't fold it on the y-axis to get two matching pieces, so it's not even, and it certainly doesn't have the rotational symmetry or origin symmetry, so it is neither even nor odd. Let's try a few more challenging examples. This is an enrichment example, which just means it's a little bit more challenging for those of you moving on to higher mathematics. Same problem, algebraically determine if the following functions are even, odd, or neither. So to algebraically determine if a function is even or odd, we always start with the same test, h of negative x. So I'm going to replace all the x's in the problem with negative x's and then simplify. A negative to an odd power is negative, so we could simplify that first term as negative x cubed. Then we have minus x. Negative x to the fifth power is negative x to the fifth, and negative 3 times negative x is positive 3x. Now, if I begin to compare this with the original, I can see lots of changes happening, but we want to be really careful here. Before we compare to the original, let's factor out our greatest common factor in both the top and the bottom. So I'm going to factor out, actually I don't want to take out the greatest common factor, I just want to factor out a negative 1 from the top. That leaves behind x cubed plus x. And I'm also going to factor a negative 1 out of the bottom. That leaves behind x to the fifth minus 3x. The purpose of doing that was to see, okay, those two negatives cancel, and our simplified rational expression is x cubed plus x divided by x to the fifth minus 3x. While it's not completely simplified because we could reduce a little bit further, it now serves the purpose of being comparable to the original. Notice it's identical to our original function. So when we plugged in negative x and simplified, we ended up with the same function that we began with. Therefore, we can say this function is even. If we graph that on our calculator, we'll see that it's symmetric about the y-axis. Let's try the next one. To determine if this is even or odd, we're going to calculate f of negative x. We can write this negative x to the third power over negative x squared minus 4. A negative number to an odd power is negative, and a negative number to an even power is positive. So now we can compare this to the original function. Notice the numerator changed sign. This is equivalent to the entire fraction changing sign. So we can see this is equal to negative f of x. Therefore, this function is odd. And you can certainly verify that it has origin symmetry by graphing it on your calculator.